Hello, Physics 1. Welcome back. This is Wednesday's lecture for week 13. All right, so moving along in chapter 7 to power, which is energy per unit time. So, power. All right, so the definition of power, which I've already written out, but I'm going to make this very explicit. Energy per unit time. And it has units of joules per second, so energy per unit time, or otherwise known as a watt. So when you look at a light bulb and you see that it has a wattage, that is telling you it's power. All right, so we finally have a way to relate time to our energy principle, because we know there's, technically speaking, this is the same amount of work as this. I mean, I applied a force over a distance. No time was factored into it. So by the way, you're running up the stairs test. You'll get to take a look at this. That would be your, test, lab. All right, so unlike the energy principle, power cares about time. Energy output in time. All right, so for instantaneous power, if a force does the amount of work F dot dr in delta t, then power is equal to F dot dr over delta t. Oh, wait. Delta r dt, we've seen you before. Hello. You can also write this as F dr dt, which is just velocity. So power is equal to force dotted with velocity. Pretty cool, huh? All right, so let's do an example. How much energy is required to run a 27-watt light bulb for 2 hours? So we know that we have 42 watt light bulb. 42 joule seconds times 2 hours, and we need to unit convert 60 minutes per 1 hour times 60 seconds per 1 minute. Energy is equal to 3.02 times 10 to the 5 joules. So very straightforward calculations for power. All right, so moving right along. Into a discussion of open and closed systems. So I told you we'd be talking about this a little bit more. This is a really important concept within physics. And, from the very beginning, I've been emphasizing that system choice really matters. What is in your system? What is in your surroundings? And being clever about this will help you solve interesting problems in really meaningful ways. But we need to really now think about, what are some bigger implications as to what can happen to your system. What type of a system have you set up? So let's look at a bank. We're going to start really simple. So this bank has people coming in, they're making deposits, and so it has $5,000 coming in, and so it has $8,000, and then we have $3,000 going out. So we've had some deposits, we're giving out some loans. This is an open system. So money is transferred in and out. So this is an open system. It can exchange energy with its surroundings. So it's both exchanging by taking in and exchanging by taking out. So let's say we have a bank holiday. So when I lived in England, these were a big deal because really, truly, banks shut down, no business can be conducted. And they were always on the oddest of days. So I'd hear about it on Friday. Oh, there's a bank holiday on Monday. Oh, there is? Cool. All right, so in this case, whatever money was in the bank, say $8,000, is staying put. It can't leave. You can't get any money in. This would be a closed system. Nothing goes in or out. Nothing can do work on it. It's just, it's going to stay put. Now, that being said, you know, you could, within this system, let's say you had 5,000 in this safe, and you had 3,000 in this safe. There's nothing to stop you from transferring an extra 1,000 into that safe. So there'd be 4,000 in this safe and 4,000 in that space. So within the system, there can be little transfers, but nothing is coming from the outside, and the total financial status of this particular bank on this bank holiday is $8,000. So another example of a open system, you have a classroom or a dorm room. Dorm rooms are very much open systems. So here's your dorm room. And so they tend to be very poorly insulated. At least my dorm rooms were. So you might have 5,000 joules coming in, heating your room. Your room is about 2,000 joules. And then you're losing heat as well. So you've got some leak there. So this is another open system. So it is allowed to exchange energy with its surroundings. Now, if it was completely insulated, then it would be a closed system. So it's just no heat can go in, no heat can go out, which has other consequences. All right, so when you set up your system, so whatever you're going to put in your system, it's often common to just draw a little dashed line around it. So then you'll have your, oh man, that's a terrible arrow. I would blame it on doing it on paper, but I think I drew them pretty poorly on the board too. But that is an arrow. So you'll have your energy coming in. This is your system. You'll be looking at the change in energy for your system, which you'll have to look at both energy coming in and energy leaving. So you're going to want to think about that boundary where you're looking at the energy transfers. So the total energy in the system is energy in minus energy out, which can be expressed as delta E system. Now, delta E system can be positive or negative. Your system could be gaining more energy or it could be losing more energy. For example, if you charge a battery, you're putting power into the system, or you're putting energy into the system, so you would have a positive change in energy for that system. However, you could run your headlights, which if you do that when your car is turned off, you will notice that you are changing the energy of your system in a very negative way. So here we have two examples of positive and negative change in energy of systems. And also, the energy of an open system is not constant, or is not necessarily constant. So you cannot make that assumption unless something else is true about it. So it can be constantly exchanging energy with the universe. So if you say your system is open, you can't say, well, my system is open, therefore delta E system is 0. No. Now, if you can set up your system in such a way that you have a closed system, so in this case, inflow is equal to outflow is equal to 0, then delta E system is equal to 0. So, and really the call about a closed system has to do with closed enough. So we've talked about the universe is the ultimate closed system. But the question is, so for example, let's say you've got a container, maybe there's hot soup in it, and you've insulated it. So we know that it's going to maintain this temperature for a very long time. Technically speaking, it will slowly radiate out some of this heat. The question is it closed enough for the duration of your problem? Closed enough for duration of problem. So sometimes we'll say this is a closed system, and it's because there's not going to be any energy exchanges for the length of time you're looking up that are measurable. So in physics, we want to know, is it a measurable difference? So, moving on, the choice of system affects energy accounted. All right, so we've kind of hinted at this a few times. So we have previously analyzed a system of potential energy looking at the ball. So we've previously looked at both a system consisting, so here's the Earth, here's the ball. We've looked at a system that consists of the two of them together, and we've looked at a system of the Earth as the surroundings and the ball as the system. And we've seen that that does change how we set up the energy principle. So we're going to extend this a little bit further. So system choice matters. And we're going to set up, this is like my favorite example, because I use something near and dear to my heart. A cross racer, her bike and the earth. So what a cross racer is, cyclocross is a form of obstacle course bike racing. So since you guys are at home right now, and I'm sure you might take a YouTube break at some point, look up cyclocross racing. It is very, very cool. But anyways, you'll be, I'm going to subject you to some terrible drawings. So you'll be on your bike. Oh, this is truly terrible. Oh boy, that's bad. All right, so you're on your bike, and then you'll have like something you need to jump over. So you'll have to get off your bike and lift it up over your head and go over the obstacle. Apparently this bike is changing size the whole time. Okay, so we're going to look at what's going to happen as the cyclocross racer gets ready to lift her bike up over her shoulder so that she can climb over an obstacle. So let's set this up. A cross racer is applying a constant force F to lift her bike of mass M through a distance h. Oh, and the reason I like this is because I've done cross racing. Through a distance h, and in the process gives her bike speed v. Okay. And we're going to consider the time in motion. So she is here, lifting up, and we're going to call it a bike because it is. She's standing on the earth, not to scale. And it's going to have been lifted up some h. So it starts on the ground and is lifted some distance h, not to scale in so many ways. All right, so just a couple of terms that we're going to use. So ER is going to be the energy of the racer. And it includes internal energy of racer plus kinetic energy, which is coming from moving the arm, plus gravitational potential energy between the earth and the racer. All right, so her energy is all of these things. So the first system we're going to look at is the racer plus the bike plus the earth. So and in this particular setup, nothing. So there we are. The initial state is bike at rest, ready to be lifted. And the final state, bike at h with speed v. All right. So our energy principle, E final, is equal to E initial plus work. So we have K final plus U final plus E racer final is equal to K initial plus UI plus energy of the racer initial plus work. All right, so let's find my zeros. So we know work is equal to 0. There's nothing in the surroundings. The kinetic energy initial is 0 because it starts at rest. The potential energy initial is 0 because it's on the surface. And so we're left with 1/2 mv squared plus mgh plus the energy of the racer final is equal to the energy of the racer initial. So the change of energy of the racer is equal to minus 1/2 mv squared plus mgh. Not that surprising. And because the racer was in the system, we could calculate the change in energy of the racer. So the energy associated with her, which includes loss of chemical energy. You burn calories when you cross race. You get hot when you cross race. Oh, I assure you do ever sweat. Increase in thermal energy, etc. So we don't know, we can't break it out more than that, but we can calculate the total change in energy. All right, so now let's look at a system of just the bike. And that means within our surroundings, we have the racer plus the earth. So there's our system. Okay, so our initial state is the bike at rest. And the final state is at h with speed b. All right, so this is the system we are now going to do the energy principle on. All right, so energy final is equal to initial energy plus any work. K final is equal to K initial plus work from the racer, she's in the surroundings, plus work from the earth, also in the surroundings. All right, so do we have any zeros? Why, yes, we do. It starts at rest. So we have 1/2 mv squared is equal to fh minus mgh. So no potential energy. There's only one object in the system. So, and I could ask you which is bigger, the force or mg? And the answer should be obvious. She's overcoming mg to lift up her bike. So F is bigger. She is overcoming to lift the bike. So by choosing the bike as the system, we can calculate delta K of the bike. So these are games you can play depending on what you're looking for. So you could ask, could we, since we've already calculated delta ER, can we relate delta E of the racer to force? And we can, so let's compare them. We have the change of energy for the racer is equal to minus 1/2 mv squared plus mgh. And we have that FH is equal to 1/2 mv squared plus mgh. So the change of energy of the racer is equal to minus FH, basically work. And the sign makes sense because she must be losing energy to exert that force to lift the bike. Okay, so let's look at one more setup here for our little cross racer. So our system is going to now be the bike plus the earth. And that means within the surroundings, we have our racer. The initial state is the bike at rest. And the final state, the bike has moved distance h and has speed v. All right, so once again, our final energy is equal to our initial energy plus work done, and the kinetic energy final plus the potential energy final is equal to kinetic energy initial plus potential energy initial plus work, which is going to come from the racer. So let's find some zeros. Starts at rest, there's a 0. Starts on the ground, there's a 0. So we have 1/2 mv squared plus mgh is equal to the force from the racer times the height. So it's consistent with what we've found before. So you could ask, does the racer do work on Earth? No. Not really. Earth hardly moves. But the whole point of doing this exercise is just to see how useful system choice could be. So when in doubt, if you are approaching a problem and you're not quite able to find what you're looking for, try a different choice of system and surroundings. But whatever you choose, you have to stick with it until you're done with it. So you can't choose mid-solution, but you can stop and say, okay, so I know this, now I'm going to switch to a different system. Anyways, that wraps up part 1 of Wednesday's lecture for week 13. Stay tuned for part 2.